So welcome to the part 2 of the MCAT General Chemistry Review video. So in this video we're going to cover things like enthalpy, delta H, how to find it using heats of formation, bond dissociation energy, Hess's law, and even calorimetry. We're also going to go over internal energy, quantum numbers, electron configuration, and lots of other topics as well, like Lewis structures, molecular geometry, and molality, molarity, phase diagrams, mass percent, intermolecular forces, Raoult's law, Henry's law, colligative properties, boiling point elevation, freezing point depression. So we're going to cover a lot of topics in this video. So let's get right into it. Let's begin. Now the first thing that we're going to talk about in our thermochemistry section of general chemistry is state functions. What do you think a state function is? A state function is something that depends on the state. It depends on the initial state and the final state. So some examples of state functions are enthalpy, delta H, entropy, delta S, Gibbs free energy, delta G, and delta E, the internal energy of a system. So those are some examples of a state function. And keep in mind, a state function doesn't depend on the path of the change. It simply depends on the initial and the final states. Now, the first thing we need to talk about is the change in the internal energy of the system. Delta E is equal to Q plus W. Q represents the heat flow into or out of the system. So let's say if the box represents the system. And let's say the temperature of the system is 100 and the temperature of the surroundings is 50. Heat flows from hot to cold. So if heat flows out of the system, is it an endothermic process or is it an exothermic process? And what is the sign of Q? Whenever heat flows out of the system, it's exothermic because heat energy is being released away from the system. And so Q is negative. Now, if heat energy flows into the system, where the system absorbs heat energy, it's said to be endothermic. For an endothermic process, Q is positive. So Q is usually measured in joules. It can be calories, but it's some unit of energy. In chemistry, energy is usually in joules. It can be kilojoules or calories. W stands for work. You need to know that 1 lowercase calorie is equal to 4.184 joules. 1 kilojoule is about 1,000 joules. And a capital calorie is 1,000 lowercase calories. Going back to this equation, delta E is equal to Q plus W. You need to know that W is positive when work is done on the system. And W is negative when work is done by the system. So when work is done on the system gains energy. Because W is positive, the internal energy of the system increases. Now, when work is done by the system must expend energy, or it has to use up energy to get something done. Whenever you want to get something done, you have to burn calories to do work. So when the system is doing work, or when work is done by the system, W is negative because it's spending energy to do work. So that's why the internal energy of the system goes down. Now, there's another equation that you need to be familiar with, and it's W is equal to negative P delta V. So pressure times the change in volume. Now pressure could be in the units of atm, and volume can be in the units of liters. Now delta E is usually in the units joules. So sometimes you need to convert from liters and atmospheres to joules. Here's the conversion that you need. 101.3 joules is equal to 1 liter times 1 atm. So we said that W is equal to negative P delta V. Now, when the change in volume is positive, that means the volume is increasing, the gas is expanding. So gas expansion occurs. And when the change in volume is negative, gas compression occurs. So let's see what this means. Let's say if we have a movable piston and let's say there's a few gas particles inside. Now, when the gas expands, it's going to apply an upward force that's going to basically push or move the piston upward. And so it's capable of doing work as the gas expands. So whenever the gas expands, an outward force is being applied. And whenever you exert a force, that force can do work. Work is equal to force times distance. So when delta V is positive, work is negative because of the negative sign. So gas expansion, whenever a gas is expanding, work is being done by the system. And so the internal energy of the system decreases. Now, to compress a gas, we need to apply a force to decrease the volume. So whenever you apply a force on a gas, work is being done on a system. And so because delta V is negative, and using the equation, it's going to be negative P times a negative volume, or negative change in volume, so the work is going to be positive. So during gas compression, or whenever you compress a gas, because you're applying a force on the gas to make the volume smaller, the work is positive. The work is being done on the gas. So let's make sure that you got the point here. So for this equation where work is equal to negative P delta V, when the change in volume is positive, gas expansion occurs, which means that W is negative. And when W is negative, that means that work is done by the system. That's your key expression. Now, when delta V is negative, the gas is compressed by an outside force. And so, because there's an external force that's compressing the gas, that's making it smaller, the work is positive. You're increasing the internal energy of the system. So therefore, when work is positive, work is done on the system, because there is an external force being applied on the system. So keep in mind, whenever W is positive, delta E goes up. Delta E is positive. So the internal energy increases. And whenever W is negative, delta E decreases, or delta E is negative, which means that the internal energy of the system decreases. And now, there are some terms that you need to be familiar with. There's three types of systems. The first system is called an open system. And then you have a closed system. And then there's an isolated system. So in an open system, matter and energy can flow into and out of the system. So heat could flow out of the system, and matter can flow into the system. So like oxygen gas could diffuse into the system. That's an open system. In a closed system, energy can flow into and out of the system. So heat energy can flow into the system. That's going to be an endothermic process. But a gas molecule like nitrogen cannot enter a closed system, nor can it leave a closed system. So in a closed system, heat can go into and out of it, or any form of energy. But mass, like matter can't flow into or out of a closed system. Now, in an isolated system, nothing can get in. So heat cannot escape an isolated system, and matter cannot enter into an isolated system. So nothing goes in and nothing comes out in an isolated system. So now let's work on a few practice problems. Calculate the change of the internal energy of a system if the system absorbs 350 joules of heat energy from the surroundings and performs 120 joules of work. So the equation that we need is delta E is equal to Q plus W. So what is Q? Q is the amount of heat energy absorbed or released. So notice that 350 joules of heat energy was absorbed. When heat is absorbed, it's endothermic, so Q is positive. So Q is positive 350 in this example. Now what about work? We know it's 120, but is it positive 120 or negative 120? So is work being done by the system or on the system? By the system means the system's doing the work. On the system means that the surroundings is doing work on the system. So notice that the system performs 120 joules of work. So that means the system is doing work. So whenever the system is doing work, it's negative 120. So you can think of this like a bank account. So when a system absorbs heat, in this case 350 joules of heat, imagine making a deposit of 350. So your account balance go up by 350. Now let's say if you want to get some work done, let's say if you want to paint your house or paint a room in your house, you got to pay money to get that work done. And so for the system to do work, it has to pay to get something done. And the currency is energy, it's joules. So for the system to do work, it has to basically write a check for 120 joules. So 350 joules went into the system, and 120 was paid out of the system to get some work done. So if you add these two values, since delta E is Q plus W, the net balance, or the net amount gained, was positive 230 joules if you add Q plus W. So 350 minus 120, that's positive 230. So the system, it banked 230 joules of energy. Determine the change of the internal energy of a system if the surroundings gain 500 joules of heat energy and performs 300 joules of work on a system. So let's write the equation. So we know that Q is 500. Is it positive 500 or negative 500? So the surroundings gain energy. If the surroundings gain heat energy, that means the system is losing heat energy. So the system is inside the box, and the surroundings is basically outside the box. So if the surroundings gain heat energy, that means the system lost it. So the surroundings gained 500 joules of heat energy. So that means Q for the system is negative 500 joules because it lost it to the surroundings. Now it also mentions that the surroundings performs 300 joules of work on the system. So if work is being done on the system, that's basically a credit. The system gains energy from that exchange. So the system is going to gain 300 joules of energy from work being done on it by the surroundings. So the change in internal energy is going to be negative 500 plus 300. So delta E is negative 200 joules. So the system lost a net of 200 joules. So imagine if you gain a deposit. Let's say if you deposited 300, but you withdrew 500. So your account has decreased by 200 bucks. In this case, the system lost 200 joules of energy overall. By the way, if you want to gain the most benefit from this video, make sure that you try the problem first before viewing the solution. And then after you work out the problem, check the answers to see if you got it right. And if not, feel free to learn from it. But if you just watch it without doing the problems, it's not going to benefit you as much as doing the problems yourself. So feel free to try this problem and see if you can get the answer. So let's begin. Delta E is equal to Q plus W. That's what we're looking for. However, notice that we have pressure and change in volume. So we got to use another equation to find work, which is equal to negative P delta V. So let's start with that equation. The pressure is 3 atmospheres, and the change in volume, final volume minus initial volume. So the final volume is 1.5 liters minus an initial volume of 1.0 liters. So this is going to be negative 3 times 0.5. And basically, 3 times 0.5 is half of 3. So that's negative 1.5 liters times atmospheres. Now notice that Q is in joules, but right now we have liters times atmospheres, so we need to convert that to joules. So the conversion factor that we need is 101.3 joules is equal to 1 liter times 1 atm. So these units cancel. So for the MCAT, we really can't use a calculator, so let's say this number is about 100. 1.5 times 100 is approximately negative 150 joules. So now we can find delta E. Since the gas absorbs 700 joules of heat energy, we know that Q is positive. So delta E is equal to positive 700 for Q and negative 150 for W. Anytime a gas expands, that means the gas is doing work. Work is being done by the system, so work is negative. 700 minus 150, well, that is 550. And so the system gains 550 joules of energy, mostly from heat, but that's the net energy that the system gained. So now let's go back to our lecture. What is the process called when a solid turns into a liquid? The process is known as melting. Think of ice. Ice is a solid. When it melts into liquid water, it melts. It's called melting. Now what about the reverse? When a liquid turns into a solid. So when liquid water turns into ice, it froze, so it's called freezing. Now what about when a liquid turns into a gas? This process is called vaporization. The sample is being vaporized. Now what about when a gas goes back into a liquid? What is that called? So when steam converts back into a liquid, this is condensation. Now perhaps you have seen this. Let's say if you pour cold water in a glass, and let's say if you place that glass in a very moist or humid environment, you can see condensation occurring on the outside of the glass. Basically, water vapor from the air, as it loses heat energy to the cold glass of water, it's going to condense and it forms water droplets on the outside of the glass container. Now, what about when a solid goes directly to the gas phase? Let's say if it skips the liquid phase and just goes straight to the gas phase. What is that called? This is known as sublimation. You've probably seen sublimation in action. Think of dry ice. Dry ice is basically the solid form of carbon dioxide. And if you pour dry ice in a table, it's never going to turn into a liquid, at least not at normal temperature and pressure conditions. If you put dry ice, it's going to go directly into the gas or the vapor phase. And that's why it's called dry ice, because it doesn't liquefy. Now, if you were to increase the pressure, it could liquefy. But at sea level, at 1 atm, it doesn't liquefy. It goes straight to the gas phase. Now, what about the reverse? Going from a gas to a solid. This is called deposition. And these are some terms that you simply need to know. Now, which of these processes are endothermic and which one is exothermic? So, melting, is that an endothermic process or is it an exothermic process? So Q, is it positive or negative for melting? Does heat need to be absorbed or should it be released from the system? Well, in order to melt ice, you have to add heat to it, not remove heat. So therefore, melting is an endothermic process because heat has to be absorbed. Now, to freeze liquid water into ice, you need to remove heat. You got to take away heat from it. And so you got to bring down the temperature of the system. Whenever you need to raise the temperature of the system, you got to add heat to it. If you want to bring the temperature down, heat needs to be removed. So freezing is an exothermic process because we need to take away heat energy from the system. Vaporization, if you want to boil liquid water into steam, you have to heat it up. So vaporization is positive, and condensation, which is the reverse of that, is negative. Sublimation, going from a solid to a gas, heat has to be absorbed, so that's endothermic. And deposition, Q is negative because it's the reverse, and that's exothermic. Now let's summarize what we've just learned. So whenever you have a solid, if you melt it into a liquid, or if you vaporize the liquid into a gas, or if you sublime the solid directly into the gas, all of these three processes are endothermic, which means that the heat or the system must absorb heat energy, so Q is positive. Now, if you wish to go in the reverse direction, from a gas to a liquid, which is condensation, or from a liquid to a solid, which is freezing, or from a gas directly to a solid, which is deposition, going in that direction, it's an exothermic process. And so, whenever you have an exothermic process, heat must be removed from the system, and so heat is being released, so it's exothermic. So what happens if we add heat energy to a system? Two things can happen. Either a temperature change can occur, or a phase change can occur. So if you heat up liquid water, the temperature could go up, or it can vaporize into steam. If you heat up ice, the temperature could go up, or ice can melt into liquid water. So one of those two things can occur. Now, if you wish to quantify the amount of heat that's absorbed or released, you can use this equation. Q is equal to MCAT, whenever a temperature change occurs. Now, let's say if only a phase change occurs, you can quantify it using this equation. Q is equal to M times delta H. Sometimes it could be N times delta H, depending on the units of delta H. Delta H stands for enthalpy. Now, delta H and Q are very similar. Q represents the heat energy absorbed or released, and it's usually in the units joules. Well, delta H is very similar to Q in that it represents the heat energy absorbed or released, but it's measured at constant pressure. Keyword, constant pressure. And also, the units are usually a bit different. Delta H in chemistry is most commonly kilojoules per mole, but sometimes you might see it as joules per gram. So, if it's in the form joules per gram, multiply by the number of grams to get Q. So use M times delta H. If it's in kilojoules per mole, multiply by the number of moles to get Q. So basically, whenever you have a temperature change, we're going to use this formula, Q equals MCAT. But whenever we have a phase change, you can use this formula, but what I'm going to do is basically calculate Q using a conversion. So if I have the mass in grams, I'm going to convert it to moles, and then convert moles into kilojoules. If I have the moles ready, I could just use this to convert it to kilojoules. Now, there's some other facts that you need to know. Whenever you add heat energy to a substance, if the temperature increases, that means that the kinetic energy of the system is increasing. So, if you're dealing with a solid, the vibrational energy of the solid goes up. The solid atoms, they're like vibrating at a greater rate. Now, for liquids, they're moving faster whenever you raise the temperature, and for gases too. Now, whenever you add heat, if a phase change occurs, the potential energy of a system is increasing. So make sure you understand the difference between the two. So let's draw the heating curve. So let's say this is for water. So on the y-axis we have temperature, on the x-axis we have heat energy in, could be in joules or kilojoules. So this is the solid phase, this is the liquid phase, and this is the gas phase. So as you add heat, notice that the temperature of the solid goes up. So during this time you're adding kinetic energy, you're increasing the kinetic energy of the system. Now what's happening here in that yellow section? By the way, the temperature at that point is 0 in reference to water. So as you add heat, what's happening is the solid is melting into a liquid. So this is a phase change. At this point, the solid and the liquids coexist. So at this point here, you have about 100% solid, no liquid. In the middle, you have 50% solid, 50% liquid, and at this point, all of the solid particles have been converted into the liquid form. So as you add heat, the potential energy of the system is increasing during this part. Now, during the third part, as you add heat, the temperature of the liquid is increasing. And whenever the temperature goes up, the kinetic energy of the system is increasing. And during the fourth part, or the fourth segment, as you add heat, the liquid is vaporizing into a gas. Now, during a phase change, the temperature is constant. So until all of the liquid molecules have been vaporized into steam, the temperature will remain constant. So therefore, the potential energy is increasing because you're breaking bonds. In the case of water, you're breaking hydrogen bonds. And then during the last segment, as you increase the temperature of the gas, the kinetic energy goes up again. So let's say if you wish to quantify how much heat is absorbed if, let's say, a 10-gram sample of water, if the temperature goes up from 25 degrees Celsius to 50 or to 75 degrees Celsius. You only need to use one equation, and that's Q equals MCAT to get the answer. But let's say if you have a 100-gram sample at negative 10 degrees Celsius, which is in the form of ice, and you want to heat it to, let's say, 50 degrees Celsius, which is liquid water. There's going to be 3 parts to this problem. You need to find Q1, which is the amount of heat that's required to raise the temperature of ice from negative 10 to 0. Then you need to find Q2, which is the amount of heat energy required to melt the ice. And then you need to find Q3, which is the amount of heat energy to raise the temperature of liquid water from 0 to 50. And then you need to add all 3 of these Q values. Now let's say if you have ice at negative 20 degrees Celsius and you wish to heat it to steam at 250 degrees Celsius. You're going to need 5 Qs to get the answer. Q1 is going to represent the heat required to raise the temperature of ice from negative 20 to the freezing point of 0, or the melting point. Q2 is the energy to melt the ice into liquid water. Q3 is the energy to raise the temperature of liquid water from 0 to 100. Q4 is the temperature required to basically vaporize liquid water into steam. And Q5 is the temperature required to heat up steam from 100 to, 200 or 250. And so you need 5 Qs in order to go directly from ice to steam. Now, there's a few more things that we need to talk about. So going back to the temperature change equation, Q equals MCAT, you need to know that M represents the mass, which is in grams. C is called the specific heat capacity, which has the units joules per gram per Celsius. And delta T is the temperature change, which is usually in Celsius. So notice that Celsius will cancel and grams will cancel, which means that Q is in joules. But now let's spend some time talking about the specific heat capacity. The specific heat capacity for liquid water, you need to know that it's 4.184 joules per gram per Celsius. So what this means is that it takes, for a 1 gram sample of water, it takes 4.184 joules to increase the temperature by 1 degree Celsius. And that's what the specific heat capacity represents. It's the amount of energy that's required in joules to heat up 1 gram of water by 1 degree Celsius. Now keep in mind though, 4.184 joules is also 1 calorie. So let's say if you get a true or false question, if they ask you, or if they make a statement, it takes 1 calories of heat energy to raise 1 gram of water by 1 degree Celsius, that would be a true statement. Now there's something else that you need to know about specific heat capacity. Now let's say if we have 100 grams of water compared to, let's say, a 100 gram sample of metal. Water has a very high specific heat capacity. It's 4.184 joules per gram per Celsius. Now, the specific heat capacity for metals, compared to water, they're fairly low. So let's say this metal has a specific heat capacity of, let's say, 0.4. So let's add 1,000 joules of heat energy to each sample. So if we add 1,000 joules of heat energy to the water and to the metal, which one will experience a greater temperature change? Is it the sample of water on the left or the metal? Now, what you need to know is that as the specific heat capacity increases, the temperature change decreases. So therefore, water is going to experience a small temperature change, whereas the metal is going to experience a very large temperature change. Now, think about this. Let's say if you put an empty metal pot on a stove. The temperature of the metal is going to increase greatly. Metals, they're very good conductors of heat and electricity. So the metal will immediately get hot. Now, if you put water on a pot, on a stove, the water doesn't instantaneously become hot. It takes some time for the water to heat up, because water can absorb a lot of energy without changing the temperature much. You see, in this case, for a 1 gram sample of metal, it takes 0.4 joules of heat energy to raise the temperature just by 1 degree Celsius only. But in the case of water, it takes 10 times as much energy to heat up that sample of water by 1 degree Celsius. So the temperature change for this sample of water is going to be 10 times as less. So let's make up a number. Let's say that the temperature of the metal increases by 20 degrees Celsius. The temperature of water might only increase by 2 degrees Celsius, because the specific heat capacity of water is a little bit more than 10 times that of the metal. So just keep this in mind. The higher the specific heat capacity, the smaller the temperature change will be for that substance. So let's work on a few practice problems. How much heat energy is required to heat 200 grams of water from 25 to 75 degrees Celsius? So let's use 4.2 instead of 4.184 for the specific heat capacity of water, just to keep the calculation simple. So this is a temperature change problem because the temperature is going up. So the equation that we need is Q is equal to MCAT, which is the test you're studying for. So the mass is 200 grams. The heat capacity, which is C, that's 4.2. The temperature change, final minus initial, 75 minus 25, that's 50. So notice that 2 times 5 is 10. So 200 times 50 is 10,000. 2 times 5 is 10, and then add the 3 zeros. So 10,000 times 4.2, this is 42,000 joules. Now sometimes you may need to report the answer in kilojoules. To convert from joules to kilojoules, simply divide by 1,000. If you need to go backwards, from kilojoules to joules, multiply by 1,000. So this is equal to 42 kilojoules because we need to divide by 1,000. So now what about this problem? How much energy is required to melt 36 grams of ice? So this is a phase change problem, and we're given the heat of fusion. The heat of fusion can be used whenever you need to freeze liquid water into ice or melt ice into liquid water. So for melting, delta H is going to be positive because it's an endothermic process, but for freezing, it's negative. So the heat of fusion is positive 6 kilojoules per mole. Now for a phase change problem, the best thing to do to get the answer is simply to convert. We can take the grams, convert it to moles, and then convert it to kilojoules. So let's start with 36 grams of water. The molar mass of water, which is going to be 2 plus 16, it's 18 grams per 1 mole. And so the units, grams, cancel. And now we can convert moles into kilojoules. There's 6 kilojoules of heat energy that correspond to 1 mole. And so now we could do the math. 36 is 18 times 2, and we have a 6 on top as well, and we have an 18 on the bottom. So these numbers will cancel. 2 times 6 is 12. So it takes 12 kilojoules to melt 36 grams of ice. Try this one. How many grams of steam is needed to release 205 kilojoules of heat energy during condensation? And we're given the heat of vaporization. So how can we do this problem? So this is another temperature change problem. So we need to convert from kilojoules to moles, and then moles to grams. So let's start with the heat energy, 205 kilojoules over 1. Now the heat of vaporization connects kilojoules to moles, so we can convert kilojoules to moles using that. So for every 41 kilojoules of heat energy that's released, 1 mole of steam condenses into liquid water. And so now we can convert moles into grams. The molar mass for water is 18 grams. So kilojoules cancel, and the units moles will cancel as well. So it turns out that 205 is 41 times 5. And we also have an 18 on top, so we can cancel the 41s on top and on the bottom. So 5 times 18 is 90. So it's about 90 grams of steam. How would you do this problem? How much energy is required to heat 100 grams of ice from -20 to steam at 250? So we're given the specific heat for ice and steam. It's about 2.03 and 2.01. So we're going to round those numbers to 2. So let's summarize what we need to do here. So ice melts at 0 degrees Celsius and water boils at 100. So we're starting at -20 and we need to get to 250. So Q1 is going to represent a temperature change from -20 to 0, and that's for ice. Q2 is going to be the phase change from ice to liquid water. Q3 represents the temperature change of liquid water from 0 to 100. Q4 is the phase change from liquid water to steam. And Q5 is going to be the temperature change of steam from 100 to 250. And then we're going to add these 5 values together. So let's begin. So let's start with Q1. So the mass, we're going to use Q equals MCAT. the mass is 100, the specific heat capacity for ice is 2, and the change in temperature, it increases from -20 to 0, or if you do final temperature minus initial temperature, that's 0 minus -20, which is 0 plus 20. So the temperature increases by 20. 2 times 20 is 40. 40 times 100 is 4,000 joules. So now let's calculate Q2, which is a phase change. Now the heat of fusion is 6 kilojoules per mole. So let's start with 100 grams of water. Let's convert it to moles. So 1 mole is equal to the molar mass of water, which is 18 grams. And then we're going to multiply that by 6 kilojoules per mole. Now, 6 goes into 18 3 times, and 100 divided by 3 is about 33.3 kilojoules. Now, we can't add joules and kilojoules together. We need to convert it into joules. To convert kilojoules into joules, you got to multiply by 1,000. So 33.3 kilojoules is 33,300 joules about. So now let's find Q3. This is for liquid water, and it's a temperature change problem. So the mass is 100. The specific heat capacity for liquid water, we're going to round it to 4.2. And the temperature change is from 0 degrees Celsius to 100 degrees Celsius, so that's an increase of 100. So 100 times 100 is 10,000, and 10,000 times 4.2, that's equal to 42,000 joules. Now Q4 is a phase change, so let's convert. Let's start with 100 grams, and it's 1 mole per 18 grams. Now the heat of vaporization for water, I forgot to write it, but it's about 41 kilojoules per mole. It was in the other problem. Now keep in mind, this is the rounded figure. The actual heat of vaporization is like 40.7, but we'll keep it simple and say it's about 41. Now we need to convert this to moles. So let's multiply by 1,000 joules per kilojoule. So how can we simplify this expression? 1,000 times 100 is basically 100,000. And 41 over 18, that's a little bit more than 2. Okay, let's use a calculator for this one. 41 divided by 18 is about 2.27. And then times 1,000 times 100. So this is equal to 200, if you round it, it's about 228,000. And then finally Q5, which is another temperature change problem, so we need to use Q equals MCAT. So the mass is 100. The specific heat capacity for steam is about 2. It's very close to ice. And the temperature change, it goes from 100 to 250 degrees Celsius. Keep in mind, 100 is the boiling point for water, and 0 is the freezing point. So that's why the temperature change is 150. It goes from 100 up to 250, so it increases by 150. 100 times 150 is basically 15,000. And 15,000 times 2, that is equal to 30,000. So to find the total heat energy that's required, we just need to add these 5 numbers. So if we add 228 plus 42, that's going to be 270, or 270,000. 270 plus 30, that's 300,000. And plus another 33,000, that's 333,000 plus 400, or plus 4,000. So this is going to be 337,000, comma 300. So that's how much heat energy is required to heat up ice into steam. Now if we want to, after we add these 5 values, we can convert the final answer to kilojoules. So to convert joules into kilojoules, divide by 1,000. So this is equal to 337 kilojoules. A 300 gram sample of an unknown metal at 150 degrees Celsius was placed in a bucket containing 100 milliliters of water at 20 degrees Celsius. Now the final temperature of the mixture was 28 Celsius. Calculate the specific heat capacity of the metal. So we have a bucket that has water and a metal was placed inside this bucket. And so the metal is at a temperature of 150 degrees Celsius initially. And the temperature of the water is only 20. So heat flows from hot to cold. So heat is going to flow from the metal into the water. So therefore, because the water is absorbing heat, let's say the water is the surroundings and the metal is the system. Because the water is absorbing heat, it's endothermic for the water. So the temperature of the water or the surroundings is going to increase from 20 to 28 because it's endo for the water. But for the metal, it's exothermic because the metal releases heat into the surrounding water molecules. And so the temperature of the metal is going to go down from 150 to 28. So this is a heat transfer problem. And we only have really two objects involved, the metal and the water. Heat flows from the metal to the water. So we need to write an equation. Q of the metal equals negative Q of the water. Now the reason why we have the negative sign is because on one side Q is going to be positive because it absorbs energy, and on the other side Q is negative because it releases energy. The metal releases energy, so Q should be negative for the metal, but the water absorbs energy, so Q is positive for that. It really doesn't matter where you put the negative sign. As long as one side is negative, it's going to work out. So Q equals MCAT. So MCAT equals negative MCAT. But of course, for two different objects or substances. So let's plug in the information that we have. On the left side, we have the mass of the metal. It's 300. We're looking for the heat capacity of the unknown metal, so we need to solve for C. The change in temperature for the metal, the final temperature is 28 minus the initial temperature of 150. And so this is equal to negative the mass of water. Now keep in mind the density of water is 1 gram per milliliter. That means that 1 milliliter is equal to 1 gram. So 100 milliliters of water is 100 grams. So that's the mass of water is 100. The heat capacity of water is, we're going to round it to 4.2. And the temperature change, final minus initial. The final is 28. The initial is 20. So on the right side, we have negative 4200 if we multiply, well actually that's 420. If we multiply 4.2 times 100. 28 minus 20 is 8. So the right side is negative. Now 28 minus 150, that's a negative number. That's negative 122. So 300 times negative 122. Well, 3 times 122 is going to be 366. And if you take 366 multiplied by 100, that's going to be 36,600. So let me make sure my math is correct. And yes, that's right. So notice that because the temperature change is negative, the left side is negative, but because of this sign, the right side is negative, so the negatives will cancel out. That's why it's important to have this negative there in the first place. So now, to solve for C, we need to divide both sides by 36,600. So C is going to be equal to 420 times 8 divided by 36,600. So we can cancel a 0, and 3660 is the same as 366 times 10. And so we have 42 times 8 on top. Now we know 42 is 7 times 6. And 366, well, we got that by multiplying 122 by 3. And 10, we can break that into 5 and 2. So notice that 3 times 2 is 6, which we can cancel with the 6 on top. So let's see if we can simplify this further. 122 is basically half of 122, that's like 61. So that's 61 times 2. We still have a 5 on the bottom. And 8, we can break 8 into 4 and 2. So at least we can cancel it too. Okay, so I don't think we can simplify this any further. So we have 28 divided by 305. So this is going to be less than 0.10 because 30 over 300 is 0.10. Let's use a calculator at this point. We can estimate the answer as being 0.1. 28 over 305 is about 0.092, which is close to 0.1. But this is the specific heat capacity of the unknown metal. So here's another problem that we can try. 100 milliliters of water at 20 degrees Celsius was mixed with 200 milliliters of water at 80 degrees Celsius. Determine the final temperature. So here is another heat transfer problem. Heat is going to flow from the hot water solution, or the hot water solvent, to the cold water solvent. So we can set up another equation like the last problem. So basically Q of water, let's say Q of A for the cold water mixture or solvent equals negative Q of B for the hot water solvent. So Q equals MCAT. And let's plug in the information that we have. Now the heat capacity for water is the same. It's 4.2, which means we can cancel C because the substance is the same. If it's different, we can't cancel C. Now, the density of water is about 1 gram per milliliter. So 1 milliliter of water is the same as 1 gram. So 100 milliliters of water is basically 100 grams of water. By the way, if you were to estimate the final temperature, what would it be? Now, if the volumes were the same, right now the volumes are different, but if they were the same, the final temperature would be right in the middle because the specific heat capacity of these two samples are the same. The final temperature will be 50, but because we have more of the hot water, the final temperature should be close to 80. So we should expect T final is going to be greater than 50, but less than 80. Delta T is the final temperature, TF, which is what we're looking for, minus the initial temperature. For the cold water sample, it's 20. And the mass of the other sample has to be 200 grams. 200 milliliters is equal to 200 grams. And the final temperature is going to be the same. And the initial temperature for that is negative 80. Now, if we divide both sides by 100, we can cancel a few zeros. So this is going to disappear as 1, and that's going to be negative 2. So on the left side, we can now open the parentheses since we have a 1 in front. So it's T final minus 20 is equal to negative 2 T final minus 80. So let's distribute the negative 2. This is going to be negative 2 TF, and then negative 2 times negative 80 is positive 160. So what we're going to do now, we're going to add 20 to both sides, and at the same time we're going to add 2 TF to both sides as well. And so let's clear away some stuff. Let's make some space. So what we now have on the left side is 3 TF. These cancel. And on the right side, this is equal to 180. So 3 goes into 18 6 times, so if you add the 0, it's going to be 60. And that's the final temperature of the mixture, or when you combine the two samples of water. As we can see, it's closer to 80 than it is to 20 because we have more of the hot water sample, and so that's why it's close to 80. So now let's talk about enthalpy, delta H. Delta H measures the amount of heat energy that flows into or out of the system at constant pressure. Now there's 4 different ways in which we could find enthalpy, or at least 4 common ways that you need to be aware of. And the first one is if you're given the heats of formation. So if you have the standard heats of formation, typically it's going to be presented in a table format. You can find the enthalpy of the reaction, the standard enthalpy of the reaction, by subtracting the sum of the heats of formation of the products minus the sum of the heat of formation of the reactants. We'll go over some examples relating to it. So that's the first way. The second is if you're given the bond dissociation energies. This could be presented in a table format, but you're not going to get like a compound. Rather, you're going to see elements, like 2 elements attached to a bond, like H attached to H through a single bond, or C double bond C, or a C triple bond C. So you're going to be given the energies of the bonds. And it turns out that to find the enthalpy of the reaction using that information, it's really the reactants minus the products. But the way you should really view it is it's the energy change when you have to put in energy to break the bonds, which is an endothermic process, so it's going to be positive. And then when the bonds are reformed to create the products, energy is released. So it's really the bonds broken minus the energy released from the bonds being formed, and that difference gives you the enthalpy change of the reactants. But if you simplify it, it works out that it's really reactants minus products. Take the bonds of the reactants subtracted by the bonds of the products, and you're going to get the right answer. Now, another way in which you could find the enthalpy change is by using Hess's law. So Hess's law, the main idea behind that is that enthalpy values are additive. So let's say if you have reaction 1, which has an enthalpy change of 100, and reaction 2 has an enthalpy change of 200. If you can add reaction 1 and reaction 2 to get reaction 3, then reaction 3 is going to have an enthalpy change of 100 plus 200, which is 300. And so that's the main idea behind Hess's law. You can use other reactions to find the enthalpy of the net reaction. And another way is to use calorimetry. So you can also estimate the enthalpy of reaction by taking Q, which is the heat released by the reaction, which is equal to negative of Q, where that's the heat absorbed by the surrounding water molecules. So it's going to be Q over N, which I'll give an example of that. So anytime you need to measure heat changes or the amount of heat that's absorbed by the surrounding water molecules, it's calorimetry. But we're going to go over these 4 different ways of calculating the enthalpy of a reaction. So let's start with the first one. So let's say that we have a reaction. NH3 reacts with oxygen to produce nitrogen gas and water. So go ahead, take a minute, pause the video, balance the reaction. So we have 3 hydrogen atoms on the left side. I'm going to put a 4. So we have 12 on the left, and then I'm going to put a 6 on the right. So we have 12 hydrogens on both sides. Now we have 4 nitrogen atoms on the left, so I need to put a 2 in front of N2. And because I have 6 oxygen atoms on the right, I need a 3 in front of O2. So the reaction is balanced. Now let's say that you're given the standard heat of formation for NH3, and let's say for NH3 it's negative 46 kilojoules per mole, and for H2O, let's say it's a negative 286 kilojoules per mole. By the way, the standard heat of formation for any pure element, like oxygen, is going to be 0. And for nitrogen, it's 0. So this For any pure element, the enthalpy, the standard heat of formation, and the Gibbs free energies can be zero for pure elements. But the entropy, delta S, it's not zero for a pure element. So now let's calculate the enthalpy change of the reaction. So delta H of the reaction, by the way, the standard enthalpy, the temperature, is 298 Kelvin. For gas laws, the standard temperature, the temperature at SDP is 273 Kelvin. So make sure you're aware of that difference. So the enthalpy is going to be the sum of the products minus the sum of the heats of formation for the reactants. So the products are N2 and water, they're on the right side, and the reactants are the 4 NH3 molecules plus the 3 O2 molecules. So now we can just plug in at this point. So the value for N2, it's a pure element, so it's going to be 0. For H2O, it's going to be 6 times negative 286, and then minus the amount for NH3, which is it's going to be 4 times negative 46, and then plus oxygen is a pure element, so it's going to be 0. And so at this point, we just got to do the math. So 6 times negative 286. Let's see if we can do this without a calculator. So 286 times 6. 6 times 6 is 36. And 8 times 6 is 48 plus 3, so that's 51. 2 times 6 is 12 plus 5, that's 1716. And let's confirm with the calculator. Make sure I didn't make any mistakes. And so that's correct. This is going to be negative 1716. And then negative 4 times negative 46, that should be a positive number. So 4 times 46 is the same as 4 times 50 minus 4. 4 times 50 is 200. 4 times 4 is 16. If you take away 16 from 200, you have 184 left over. So this is plus 184. And so now we have to add these two numbers. So negative 1716 plus 184, that's negative 1532. And so the units is going to be kilojoules per mole. So that's how you can calculate the enthalpy change of a reaction using heats of formation. Now you might be wondering, well, what is the heat of formation? So the heat of formation is basically the enthalpy change of a specific type of reaction. It's a reaction where you have a compound on the right side and pure elements on the left. It's the enthalpy change of a reaction where a compound is formed, or in 1 mole of a compound, it's formed from its elements in a natural standard state. So let's say if we wanted to write the heat of formation for ammonia, NH3. So what we need to do is put NH3 on the right side, and the coefficient has to be 1. We can't change it. We can't make it a 2, we can't make it 1/2, we can't put a 3 in front of it, it has to be 1. So in this reaction, to balance it, you may have to use some fractions. Now, on the left side, we need to separate nitrogen and hydrogen. We need to write them in their elemental form. Nitrogen, in its natural standard state, exists as a diatomic element. It's N2. And hydrogen gas is also diatomic. Now, to balance it, we may need to use fractions. So what number do we need to put in front of N2 to balance this reaction? Notice that we have 1 nitrogen on the right side. So 1 divided by 2 is 1/2. And what number do we need to put in front of hydrogen? So 3 divided by 2 is 3/2. And now the reaction is balanced. So that's how you can write the heat of formation, the reaction for the formation of a compound from its natural elements in their standard states. So let's go ahead and calculate the enthalpy change of this reaction. So the enthalpy change of a reaction, we said it's products minus reactants. The products is NH3, and the reactants are 1/2 N2 plus 3/2 H2. Now the heat of formation for NH3 is, we said it was -46. And for any pure element, it's going to be 0. So for N2, it's 0, and for H2, it's 0. So notice that the heat of reaction is equal to -46, which is equal to the heat of formation of NH3. So the heat of formation equals the heat of the reaction whenever you have a reaction where a compound is created from its elements in their natural states. Whenever you have such a reaction, the enthalpy change of that reaction equals the heat of formation of that compound. As you can see, we got -46. So the enthalpy change for this reaction is -46. Now what about for the other compound, H2O? So let's put H2O on the right side, and we have to put a 1 in front of it. We can't change that number. So if we separate H2O into its elements, it has hydrogen, which exists as H2, and oxygen gas, which is diatomic, it's O2. So the hydrogen atoms are already balanced. We don't have to change it. But we only have one oxygen atom on the right side. So 1 divided by 2 is 1/2. So let's put 1/2 in front of O2. So now it's balanced. And the heat of formation for H2O was -286, which is the same as the heat for this reaction, because if you do products minus reactants, it's going to be H2O, which is -286, minus 0 for H2 and 0 for O2. So the enthalpy change for this reaction is -286. Now, how can we use Hess's law? How can we adjust these two equations such that we can get the enthalpy change of this reaction? 4NH3 plus 3O2, which turns into 6H2O and 2N2. How can we adjust those two reactions to get the enthalpy change of this third reaction? The process of doing this is called Hess's law. So what we need to do is focus on the right reactants and products. There's some reactants and products that you don't want to focus on. So the two reactions that we want to add, which is the first and the second one, you don't want to focus on any reactants or products that are found in both reactions. Notice that hydrogen is found in the first two reactants or reactions. We don't want to focus on that. So let's focus on NH3. We have one NH3 molecule on the right, but here we have 4. So we need to change the first reaction to make it look like the net reaction. So we need to reverse the first reaction so that NH3 will be on the left side, and then we need to multiply it by 4. And so we need to change this. We got to multiply by 4, and anytime you reverse the reaction, you have to change the sign. So it's going to go from negative to positive. So we're going to have 4 NH3, and we had 1/2 N2. 1/2 times 4 is 2. So it's going to be 2N2. And then we had 3/2 H2. 3/2 times 4 4 times 3 is 12, divided by 2 is 6. So it's going to be 6H2. And so now we need to multiply negative 46 by 4. And we're going to have to make it positive. So we calculated that value already. We did 50 minus 4 times 4. So that was like 200 minus 16, which was 184. Or you could do 4 times 40, which is 160. And 4 times 6 is 24. 160 plus 24 is 184. You can calculate that way. But because we reversed it, it's going to be positive 184. Now, for the next reaction, water is on the appropriate side, so we don't have to reverse it. However, we do have to multiply it by 6. So let's get rid of this number, and let's put a 6 in front of it. And we're going to put a 6 in front of H2. 1/2 times 6 is basically 3. So this is going to be 3O2. So now we got to multiply negative 286 by 6, which this time I'm going to use a calculator. And that's negative 1716. So let's get rid of this, and let's put that here. So now, let's get rid of this too. But remember this reaction, feel free to write it down. We need to add the two reactions and get this same exact reaction. So, when we add these two reactions, what cancels? Notice that we have 6 H2 molecules on the right and 6 H2 on the left. So they will cancel. And let's put our arrow. Nothing else cancels. So on the left side, in the first reaction, we have 4 NH3. So that's simply going to drop down to the left side of the net reaction. So let's put that 4 NH3. Now on the left side of the second reaction, we have 3O2. So that's going to fall down to the left side. So let's add plus 3O2. And here we have 2N2. It's on the right side of the first reaction. So that's going to go here. And on the right side, we also have 6 H2O molecules, which we're going to put it in the right side of the net reaction. So notice that this reaction is the same as the reaction we had before. So according to Hess's law, if you add reaction 1 and reaction 2 to get reaction 3, to find the enthalpy change of reaction 3, you can add the enthalpy change of reactions 1 and 2. So 184 plus negative 1716 is equal to negative 1532, which is the answer that we had in the last problem. So that's how you can use Hess's law to estimate the enthalpy change of a reaction. So now let's work on some examples just so that you can get more practice with what we've considered. So let's say if you have a compound, calcium carbonate, how would you write the reaction that corresponds to the heat of formation for calcium carbonate? To write that reaction, put the compound on the right side and put a 1 in front of it. By the way, feel free to pause the video and try this example yourself. So we have 3 elements in this structure. We have calcium, which exists in its natural standard state as Ca. Carbon is not diatomic, it's just elemental carbon. But oxygen exists as a diatomic molecule. And so we need to balance. We need to balance the reaction. So the calcium and carbon atoms are the same. But notice that we have 3 oxygen atoms on the right side, 2 on the left. So 3 divided by 2 is 3 over 2. And so now you know how to write the heat of formation or the reaction that is associated with the heat of formation. Try this problem. Let's say if you have this reaction. Ethanol reacts with oxygen gas to produce carbon dioxide plus water. So this is a combustion reaction. And the heat of reaction for this particular reaction is called the heat of combustion because it's a combustion reaction. Now let's say if you're given the heats of formation for every compound in this reaction. So let's say for ethanol, the heat of formation is negative 280. Let's use a nice round number. And for CO2, let's say it's about negative 390. And for water, the heat of formation is negative, let's say 290. Now, keep in mind though, in a typical problem, this information is going to be presented in a table. But I'm just going to put the numbers next to their respective compounds. So for the sake of practice, go ahead and try it. Pause the video and see if you can calculate the enthalpy change of the reaction using the equation products minus reactants. So delta H is going to equal the products, which is 2CO2 plus 3H2O, and then minus the reactants, which is C2H5OH plus the 3 O2 molecules. So for CO2, the value is negative 390, and for H2O, it's negative 290, and for ethanol, it's negative 280, and for oxygen, it's simply 0. So 2 times negative 390, 2 times 39 is 78. So this is going to be negative 780. 3 times 29. Well, 29 is 30 minus 1. So 3 times 30 is 90. And 3 times 1 is 3. 90 minus 3 is 87. So this is going to be negative 870. And then we have two negatives, which is going to turn into a positive. So plus 280. Let's add negative 780 plus 280. Negative 78 plus 28, that's going to be negative 50. 28 minus 78 is negative 50. So this should be negative 500. And then minus 870, that's going to be negative 1370. So let me confirm it with the calculator. And yeah, that is correct. So that's the enthalpy change for this reaction in kilojoules per mole. Now, let's say if we have two reactions, NO2 plus O2, which turns into NO plus O3. And the enthalpy change for this reaction, let's say it's positive 200. And for this, the next reaction is going to be O3, and that turns into 3 over 2 O2. And the enthalpy change is going to be negative 140. So using these two reactions, calculate the enthalpy change for this reaction. 2NO plus O2, which turns into 2NO2. So we need to know what to focus on and what not to focus on. So NO2 is only found in the first reaction. Let's focus on that. So notice that it's on the right side and there's a 2 in front of it. That tells us that we need to reverse the first reaction and multiply by 2. So let's get rid of this. And so we had NO and O3 on the right side. So we're going to change it. We're going to put it on the left side, and let's put a 2 in front of it. Now, on the left side, we had NO2 plus O2. So we're going to multiply by 2 and put it on the right side. So 2NO2 plus 2O2. So now we have to change the enthalpy for that reaction. So because we reversed it, the sign is going to change from positive to negative. And we multiplied by 2, so it's going to be negative 400. So now we have to change the second reaction. Now notice that we have O3 in both reactions, and we have O2 in both reactions. So we have no choice. We have to use one of them. But let's focus on O3. The reason being is O3 is not in the third reaction. And the only way that can happen is if it's canceled when we add the first two reactions. So if we're going to cancel it, we need to adjust it. Notice that we have O3 on the left side. For it to be canceled, this O3 must be on the right side, and we need a 2 in front of it. So that tells us that we need to reverse the second reaction and multiply it by 2. So on the right side, we had 3 over 2 O2, but if we multiply by 2, 3 over 2 times 2, the 2's cancels, and you're going to get 3. So we're going to have 3 O2 on the left side. Now we had one O3 molecule on the left, so it's going to be 2 O3 on the right when we multiply it by 2. So now because we reversed the reaction, the enthalpy for that reaction is going to change from negative to positive. And because we multiplied by 2, 140 times 2 is positive 280. So now let's add the reactions, and let's see if we're going to get the net reaction. So notice that O3 cancels because they're exactly the same and they're on opposite sides. So NO is going to drop down. And notice that we have O2 on both sides, but we have 3 on the left, 2 on the right. So therefore, subtract both numbers by the smaller of the two numbers. So if we subtract the right side by 2O2 and the left side by 2O2, these will cancel, and 3 minus 2 is 1. So we're going to get 1O2 on the left side. And on the right side, this is going to just fall down, and so it's going to be 2NO2. Notice that it's the exact same of this reaction. They are identical. So we have the net reaction. So we can use Hess' law, and we can add the enthalpies of the first two reactions. Negative 400 plus 280. How much is that? Well, what's 280 minus 400? 28 minus 40 is negative 12. So 280 minus 400 is negative 120. And so that's the enthalpy change of the net reaction. So now let's spend some time talking about how to estimate the enthalpy change of the reaction using bond dissociation energies. So consider this reaction. Hydrogen gas reacts with chlorine gas to produce hydrochloric acid. To balance it, we just need to put a 2 in front of HCl. Now let's say if you're given the bond dissociation energies. So for hydrogen, let's say it's positive 436. And for chlorine, let's say it's 242. And for hydrochloric acid, let's say it's 432. So to estimate the enthalpy change of the reaction, it's going to be the difference between the energy absorbed when you break the bonds and the energy that's released when the bonds form. So whenever you break a bond, it's an endothermic process. And whenever a bond forms, it releases energy that's exothermic. So it's the amount of energy required to break the bonds. Now this is going to be positive because it's endothermic. And plus the energy that's released. Now because whenever energy is released, it's negative, we're going to put a minus sign. So this is the amount that's released whenever the bonds form. So therefore, you need to break the bonds of the reactants. So it's going to be the bonds of the reactants minus the bonds of the products, because you have to break the bonds of the reactants, and then the bonds that leads to HCl, the bonds that form, are the bonds that are in the product, so to speak. So that's why it's like reactants minus products. So the energy of the reactants is going to be, we need to break the hydrogen bond and the chlorine bond. So that's for the reactant side. For the product side, 2 HCl bonds will form. So let's do the math. So it's 436 for hydrogen, 242 for chlorine, and then minus 2 times 432. So 436, well, to make the math easier, let's write it out. This is 436 plus 242, and then 2 times 432, that's just 432 minus another 432. The reason why I'm doing it this way is because it's fairly easy to subtract 436 by 432 because they differ by 4. So then it's 4 plus 242 minus 432. So this is 246 minus 432. So let's subtract it backwards. So 432 minus 246. We need to borrow a 1 from the 3. So this is going to be 2, and then the 2 on the right is going to be 12. 12 minus 6 is 6. Now 4 is larger than 2, so we need to borrow a 1 from the 4. So 12 minus 4 is 8, and 3 minus 1 is 2, so this should be negative 186. So if we type that in the calculator, 246 minus 432 is negative 186. If you subtract it backwards, just make sure to add the negative sign. So this is the enthalpy change of the reaction. That's how you can calculate it using bond dissociation energies. So let's understand that reaction using Hess's law. So hydrogen gas, which I'm going to write as HH, it's a reactant in the last reaction, and for it to react, we need to put an energy to break the bonds between the two hydrogen atoms. Once we break it, it's going to exist as a radical. So we're going to have 2 hydrogen radicals. And the bond energy, the average bond energy, was 436. And whenever you break a bond, it's an endothermic process because you have to add heat to it. You have to put heat in to the reactant to break the bond. So therefore, the energy change for this reaction is positive 436. Now for the next one, we also need to break the bonds between the 2 chlorine atoms. And so when we do that, each of them is going to turn into a radical. Now the enthalpy change for this reaction is going to be positive 242 because this is also endothermic. Now, to form a bond between the hydrogen radical and the chlorine radical, that is going to be an exothermic process. Whenever you form a bond, energy is released. And so we're going to get HCl. And the bond association energy for HCl was 430. It was 432. But it's going to be negative 432 because the bond is forming, and so that's exothermic. Whenever a bond forms, it releases energy. But keep in mind, we need 2 HCl bonds, so we got to write another reaction that's similar to the last one. Because if these 2 react here, then these 2 must react in what I'm about to draw, so that the reaction is balanced. And so this is going to release another negative 432 kilojoules of heat energy. So let's add these reactions. So to add these reactions, let's do some canceling. We can cancel the hydrogen radicals, and we can cancel these 2. We can also cancel a chlorine radical as well. So what we have left over is H2 on the left side plus Cl2, and we have 2 HCl molecules, which is the net reaction. So according to Hess's law, we need to add the enthalpy changes for the individual reactions. So let's use a calculator this time. 436 plus 242 minus 432 minus 432. We're going to get the same answer, which is negative 186. So now you understand how Hess's law plays an important role in understanding the calculation of bond dissociation energies, or using bond dissociation energies to calculate the enthalpy change of the reaction. Now let's say if you're given the bond dissociation energies for CH, and let's say that's 413, and for C double bond O, let's say it's 495, and for the double bond between the two oxygen atoms, let's say it's, well actually, this is supposed to be 495. This is 799. And finally, for the OH bond, let's say that's 463. So, using this information, using these bond dissociation energies, calculate the enthalpy change for the combustion reaction of methane. So you need to know what methane is. Methane is an alkane with one carbon. It's CH4. So for a combustion reaction, the hydrocarbon is going to react with oxygen gas, and it's going to produce CO2 and water. Now the first thing we need to do is balance the reaction. We have 2 hydrogen atoms on the right side. We have 4 on the left. So we need to put a 2 in front of H2O and a 1 in front of CH4. Now we have 1 carbon atoms on both sides, so we don't have to worry about that. But we have a total of 4 oxygen atoms on the right side. So we need a 2 in front of O2. So now the reaction is balanced. Now, it might be useful to draw the Lewis structures for each element and compound that's in this reaction. Methane looks like this, is CH4. So as you can see, we have 4 carbon-hydrogen bonds. Oxygen exists as O2, and it's a double bond. Carbon dioxide looks like this, and water looks like that. So therefore, when we use the equation delta H of reaction is equal to the products minus reactants. For bond dissociation energy, it's going to be reactants minus products. So it's going to be CH4 plus 2O2. Those are the reactants minus the products. CO2 plus 2H2O. So now we got to write it in terms of bonds. Now we drew methane. Methane contains 4 CH bonds. Now every oxygen molecule contains a single double bond between the 2 oxygen atoms. So because there's 2 oxygen molecules, we have 2 double bonded oxygen atoms. And then carbon dioxide, which we drew like this, a single carbon dioxide molecule has 2 C double bond O bonds. So we're going to write 2 C double bond O. Now water, a single water molecule has 2 OH bonds. So therefore 2 water molecules must have 4 OH bonds. So now let's plug in into the equation. Let's get the answer. So the value for the carbon-hydrogen bond is 413, and for the oxygen bond it's 495, and then minus the bonds that are forming. So for the carbon-oxygen bond, it's going to be 799 times 2. And for the OH bond, it's 463, but times 4. So 4 times 413, 4 times 4 is 16. So 4 times 400 is 1600. 4 times 13, that's 52. So this is going to be 1652. Now 2 times 495. 495 is 500 minus 5. 2 times 500 is 1,000. 2 times 5 is 10. 1,000 minus 10 is 990. Now 799 is 800 minus 1. 2 times 800 is 1600. 2 times 1 is 2. 1600 minus 2 is 1598. So now what about 4 times 463? 4 times 400 is 1600 because 4 times 4 is 16. We got to add the two zeros. 4 times 60. We know 4 times 6 is 24, so 4 times 60 is 240. So if we add 1600 and 240, we're up to 1840. And 4 times 3 is 12, so 1840 plus 12 must be 1850. But don't forget to, it's 1852. But don't forget to distribute the negative sign. So both numbers on the right is negative. But let's confirm these numbers with the calculator. Just to make sure I didn't make a mistake. Mistakes do happen. Okay, so these numbers look good. So now let's add these four numbers without a calculator, but then we'll check our answer with a calculator. Because on the MCAT, I don't believe you're allowed to use a calculator. So you have to practice your math skills. So let's add 1652 plus 990. So 2 plus 0 is 2, 5 plus 9 is 14, carry the 1 over. 1 and 9 is 10, plus 6, that's 16. Add these two, that's 2. So we get 2642. Now let's add the two negative numbers, but we're going to add them as if they're positive, and we'll add the negative sign later. So 1598 plus 1852. 2 plus 8 is 10, carry the 1 over. 1 and 9 is 10 plus 5, that's 15. 5 and 8 is 13 plus 1, that's 14. And 1 plus 1 plus 1 is 3. So this is 3450, but negative 3450. So now we need to combine these two numbers. So let's subtract the larger number from the smaller number. Because the larger number is negative, overall our answer should be negative. So now let's subtract. 2 is greater than 0, so we need to borrow a 1 from the 5. So this is going to be 4. And then 10 minus 2 is 8. 4 minus 4 is 0. And the 6 is larger than the 4, so let's borrow a 1. So this is going to turn into 2, and that's going to be 14. So 14 minus 6 is 8, and 2 minus 2 is 0. So this should be negative 808. So let's check with the calculator. It's 2642 minus 3450 is indeed negative 808. So that's the enthalpy change for the reaction using bond dissociation energy. So let's try this problem. 30 grams of sodium hydroxide was dissolved in water. The temperature increased from 20 to 70 degrees Celsius. Estimate the enthalpy of the reaction for the dissolution of sodium hydroxide. So let's write the reaction. Sodium hydroxide, which is a solid, is dissociated into sodium and chloride ions. And so they're going to be dissolved in water. So our goal is to estimate the enthalpy change of this reaction. So we can't use Hess's law because we don't have the enthalpy change for other reactions that can add up to this one. And we can't use heats of formation because we're not given the data for NaOH or for these aqueous ions. And we can't really use bond dissociation energy. So the other way is simply to dissolve this in water and see how much energy is absorbed by the surrounding water molecules. So what we need to do is find out the heat released by the reaction and divide it by the moles. Typically, delta H is in kilojoules per mole. And so we need to find Q in kilojoules and divide it by the moles, and we can estimate the enthalpy change for this reaction. And so this is using calorimetry, which measures the amount of heat that flows into or out of a system using water. By the way, this reaction, the dissolution of sodium hydroxide, is it an endothermic reaction or an exothermic reaction? Now, whenever the temperature of the water goes up, the reaction is exothermic. But if the temperature of the water were to go down, the reaction will be endothermic. Now let's understand why. So let's say if we have like a container with water. Let's say it's a closed system, or better yet, an isolated system. You need to understand that the surrounding water molecules, well, the water molecules represents the surroundings. The reaction is the system. Let's say this is the reaction where sodium hydroxide is dissolving. So that's the system. Now, the temperature of the water increased. It went up from 20 to 70 degrees Celsius. That means that the water, it gained energy if the temperature went up. So for the water, it was an endothermic process because the water absorbed heat. Now, where did the water absorb the heat from? The heat came from the reaction. Heat flowed out of the system into the surroundings, and that's why the temperature of the water went up. It absorbed the heat from the reaction. Now, the reaction is the system. That means the system is releasing heat. So it's exothermic for the reaction. So to review, whenever the temperature of the water goes up, it's endothermic for the water, which is the surroundings, which means that the system, the reaction, it's exothermic because the reaction released energy and the water absorbed it, increasing the temperature. Now, if the temperature of the water were to go down, it's exothermic for the water because the water is releasing heat, and that means that the reaction, the system, is absorbing heat, so it's endothermic for the system. So anytime the temperature goes up, the reaction is exothermic, and when the temperature goes down, the reaction is endothermic. So now that we understand that, we know that delta H, our final answer, has to be negative because the temperature of the water rose. So now, here's what we need to do. The first thing we need to do is find the amount of heat absorbed by the water, which is equal to MCAT. Once we have that, we can find the amount of heat released by the reaction, which is equal to negative the amount of heat released by the water, or absorbed by the water. So if the water absorbs, let's say, 100 joules of heat energy, the reaction releases negative 100 joules of heat energy. So that's why we have the negative sign. And then the enthalpy change of the reaction is going to be Q of the reaction divided by N. So those are the steps that we're going to take to get the answer. So let's begin. Let's calculate how much heat energy was absorbed by the water molecules. So the volume is 100 milliliters. Keep in mind the density of water is 1 gram per milliliter, which means that 100 milliliters of water has a mass of 100 grams. And let's use the specific heat capacity for water as 4.2 instead of 4.184 to keep the calculation simple. Now the change in temperature, final minus initial, 70 minus 20, that's an increase of positive 50. So now let's multiply. 100 times 4.2 is, 100 times 4 is 400. 0.2 times 100 is 20. So this is 420. And 420 times 50. Well, 420 is basically 42 times 10, and 50 is 5 times 10. So what's 5 times 42? 5 times 40, well, 5 times 4 is 20. 5 times 40 is 200. And 5 times 2 is 10, so 200 plus 10 is 210. So this is going to be 210 times 10 times 10. 210 times 10 is 2100 times another 10, that's 21,000. So this is equal to 21,000 joules. And as you can see, it's positive because the temperature increased. So the water absorbed heat energy, so it's endothermic for the surroundings. So therefore, Q of the reaction is equal to negative Q of water, so this is negative 21,000 joules. Now typically, delta H is usually in kilojoules per mole. So let's divide this by 1,000 to convert it to kilojoules. So this is negative 21 kilojoules. Now the last thing we need is the moles of sodium hydroxide. We have the mass, so let's convert it. 30 grams of NaOH. Now the molar mass of NaOH, it's 23 for Na, 16 for O, 1 for hydrogen, so that's 40. So there's 40 grams of sodium hydroxide in 1 mole. So if that's the case, how many moles are in 30 grams of sodium hydroxide? It has to be less than 1. We can cancel the 0, so we have 3 over 4, which as a decimal is 0.75. So we have 0.75 moles of sodium hydroxide. So now we can estimate the enthalpy change of the reaction. It's going to be Q over N, so negative 21 kilojoules divided by 0.75. So let's put 0.75 back into its fraction form, which is 3/4. So this is the same as negative 21 divided by 3 over 4. Let's multiply the top and the bottom by 4. So here the 4's will cancel. And so on top we have 21 times 4, and on the bottom we have 3. Now 21, we can break that into 7 times 3. And we also still have the 4 on top, so we can cancel the 3's. So then this is just negative 7 times 4, which is negative 28. So negative 21 divided by 0.75 is negative 28. So this is 28 kilojoules per mole. So that's how you can estimate the enthalpy change of a reaction using calorimetry, or using the amount of heat that's absorbed by the surrounding water molecules. Now let's spend some time talking about thermochemical equations. These are equations that have the enthalpy change of the reaction associated with them. So here's an example of a thermochemical equation. Now you might be wondering, okay, why are we going over this? And you'll see in just a minute. Now sometimes the enthalpy change in a reaction might be associated with delta H. You'll see delta H there. Sometimes you won't see it. So let's say if you have A plus C turns into F, and then you might have like plus 300. And it doesn't say delta H equals 300. It's just 300 kilojoules. Other times, you might see the enthalpy change on the left side. Now the question is, what does it mean? So if delta H equals a positive number, regardless of what side it's on, it's endothermic. If delta H equals a negative number, it's exo. Now, in the last two reactions, delta H is not present. We simply have a number. So, if the energy, or the number in front of kilojoules, if it's on the right side, that means energy is being released, it's being produced in a reaction, so therefore it's an exothermic process. If it's on the left side, it's endo. Notice that it's always positive on the right side or on the left side. So you can't use a sign to tell. You have to look at what side it's on. If it's on the right side, it's exothermic. That means delta H is negative 300 kilojoules. If it's on the left side, it's endothermic. Delta H is positive 400 kilojoules. And I want to make sure that I cover that fact because that might be important when you take the test. Try this one. The enthalpy of combustion for benzene is negative 3300 kilojoules per mole. Calculate the amount of heat energy released if 156 grams of benzene reacts with excess oxygen gas. So let's write the combustion reaction. So we have benzene, which is C6H6, and it reacts with oxygen gas. And the products of combustion are always CO2 and H2O. So to balance it, what do we need to do? Well, notice that there's 6 hydrogen atoms on the left side, and if we put a 3 in front of H2O, the number of oxygen atoms will be odd. To avoid that, let's start by putting a 2 in front of benzene. So we have 12 carbon atoms on the left side, so we need a 12 in front of CO2. And notice that we have 12 hydrogen atoms, so therefore we need a 6 in front of H2O. So notice that we have 24 oxygen atoms from the 12 CO2 molecules, plus 6 oxygen atoms from the 6 water molecules. 24 plus 6 is 30. 30 divided by 2 is 15. So we need to put a 15 in front of O2. So now the reaction is balanced. So now, what is the enthalpy change for this reaction? Is it negative 3300 or is it something else? Now, if we had a 1 in front of C6H6, then it would be negative 3300 kilojoules, because it's kilojoules per mole. So if 1 mole of benzene reacts with excess oxygen gas, 3300 kilojoules of heat energy will be released. But notice that we have a 2 in front of C6H6. So if 1 mole releases 3300 kilojoules of heat energy, 2 moles must release negative 6600 kilojoules of heat energy. So therefore, as a thermochemical equation, we can put negative 6600 kilojoules for this reaction. So what we need to do to solve this problem is we need to use stoichiometry. We need to convert grams to moles and moles to kilojoules. So you need to understand the mole-kilojoule ratio. So the energy that corresponds to this reaction, as we mentioned, is 6600 kilojoules for every 2 moles of benzene that reacts. So whenever 2 moles of benzene reacts, negative 6600 kilojoules of heat energy will be released. Now notice that we have a 15 in front of O2. So in terms of oxygen, when 15 moles of O2 reacts, negative 6600 kilojoules of heat energy will be released. Now let's say if we have moles of CO2. For every 12 moles of CO2 that reacts, 6600 kilojoules of heat energy will be released. So, do you see where I'm getting at here? Make sure you understand that. So, let's start with 156 grams of benzene. And let's convert it to moles. So the molar mass for benzene is going to be 6 times 12 plus 6. 6 times 12 is 72, plus 6, that's 78. So there's, for every 78 grams of benzene, there's 1 mole of benzene. Now we can convert from moles to kilojoules using this number. So for every 2 moles of benzene that reacts, 6600 kilojoules of heat energy will be released. So it turns out that 78 times 2 is 156. So these numbers will cancel with the 156 on the top. So the final answer for this problem is simply negative 6600 kilojoules of heat energy. That's how much energy is going to be released in this reaction. Here's another reaction, or another problem. Let's say if SO2 reacts with O2 to produce SO3. And let's put a 2 in front of those and a 1 in front of O2 to balance the reaction. And let's say that this reaction releases 190 kilojoules of energy. Now, because the kilojoules is on the right side and there's no delta H, this is an exothermic reaction. So, let's say the question asks you to do this. Calculate the amount of sulfur trioxide produced if 742 kilojoules of heat energy was released. How would you do it? So, what we need to do is convert kilojoules into grams of sulfur trioxide. So let's start with the energy change that we have, 742 kilojoules. Now, notice that the coefficient is 2. So for every 2 moles of sulfur trioxide produced, 190 kilojoules of heat energy will be released. So we can convert from kilojoules to moles using that fact. So for every 190 kilojoules of heat energy released, 2 moles of sulfur trioxide will be produced. So now let's convert moles of SO3 into grams. So we need to find the molar mass. For sulfur, the atomic mass is 32, and for oxygen is 16. 16 times 3 is 48, and 48 plus 32 is 80. So there's 80 grams of SO3 per 1 mole of SO3. So as we can see, the kilojoules cancel, and the moles of SO3 cancel as well. So now let's work out the problem. So we can cancel a 0. And so it's 742 times 2 times 8 divided by 19. So 8 times 2 is 16, and 742 times 16. Let's see what the answer for that is. So 2 times 6 is 12. Carry a 1 over. 4 times 6 is 24, plus 1 is 25. Carry the 2 over. 6 times 7 is 42. Plus 2, that's 44. So add a 0. Let's get rid of these numbers. 1 times 2 is 2. 1 times 4 is 4. 1 times 7 is 7. So if we add, it's going to be 2, 7, 8, 11. So 742 times 16, if you use a calculator, is indeed 11,872. So how can we divide 19 into 11,872? So we might need some space. So let's move this up here. So how many times does 19 go into 118? So 19 plus 19, that's 38. If you add it again, it's 57. Plus another 19, that's going to be 76. Plus another one, 95. Plus another one, that's going to be 114. Plus another one, that's 133. So 133 is too much. So 19 goes into 118 6 times. So 6 times 19 is 114. And so the difference is 4. Let's bring down to 7. So 19 goes into 47 2 times. 3 times is too much. 3 times is 57. It exceeds 47. So let's put a 2. 19 times 2 is 38. And if we subtract 47 by 38, that is going to give us a 9. So let's bring down the 2. How many times does 19 go into 92? 5 times is too much. 95 exceeds 92. So it goes into it at least 4 times. So 19 times 4 is 76. And 92 minus 76, that's 16. So let's add a 0. So how many times does 19 go into 160? This is really 16.0, but we're going to treat it as if it's 160. So we know it can go into it more than 7 times because we can add another 19 to 133. And if we do, it's going to be 152. Now, if we add 19 to 152, it's going to exceed 160. So we know that 19 goes into 162 at least 8 times. And even though, so 160 minus 152, I'm out of space, we're going to have a remainder of 8. But we can stop here. 624.8 is close enough. We can round our answer and say it's about 625 grams. So if we confirm our answer, if you use a calculator, 11,872 divided by 19 is about 624.842. But this is a good approximation, so we can stop here. So now you know how to convert kilojoules to grams if you're given a thermochemical equation. So now let's go over the different forms of electromagnetic radiation. The first one you need to know are radio waves. After radio waves, there are microwaves, and then you have infrared, and then you have visible light. Perhaps you heard of the expression Roy G. Biv: red, orange, yellow, green, blue, and violet. After violet, there's ultraviolet, and then you have X-rays, and then after X-rays, I'm just going to leave X for X-rays. Then there's gamma rays, which I ran out of space, so this is the gamma symbol. Going to the left, radio waves have the longest wavelength. So wavelength increases as you go to the left. And as you go to the right, the energy of the radiation increases. So keep in mind, light is carried by photons. So the energy of the photon increases as you go to the right. So gamma rays has the most energy compared to what's listed here. And frequency also increases as you go to the right as well. So let's say if you want to know which one has more energy, microwaves or infrared rays, what would you say? Now, since infrared is to the right of the microwaves, infrared radiation has more energy than microwave radiation. Now, which one has a higher frequency, yellow light or green light? Green is to the right of yellow, so as you go to the right, frequency increases, so a green photon has a higher frequency than a yellow photon. Now, which one has a longer wavelength, ultraviolet light or X-rays? Wavelength increases to the left, so ultraviolet light has a longer wavelength than X-rays. So you may see questions like that, so if you know this chart, you can answer any of those types of questions. Now, there are some equations that you need to know. The speed of light is equal to the wavelength times the frequency. C represents the speed of light, and the speed of light is 3 times 10 to the 8 meters per second. Lambda is the wavelength, and the wavelength is in meters. V is the frequency, and the frequency is measured as s to the minus 1 or hertz, Hz. Now, sometimes you might be given the wavelength in nanometers. Keep in mind that 1 nanometer is equal to 1 times 10 to the minus 9 meters. So let's say if the wavelength is 420 nanometers, you can do a quick conversion. You can replace nanometers with 10 to the negative 9 meters. So whenever you're using this equation, if you're given the wavelength in nanometers, you can write this as 420 times 10 to the negative 9 meters. So just replace this part with 10 to the minus 9. Now, there's another equation that you need to be familiar with, and it's this equation. The energy of a photon is equal to Planck's constant times the frequency. Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. Now, so that's how you can find the energy of a photon if you're given, or if you know the frequency of a photon. Now, from the other equation, we know that C equals lambda V. So if you solve for V, the frequency is the speed of light divided by the wavelength. So you can find the energy of a photon directly from the wavelength if you use this equation, hc divided by lambda. So basically, we replace V with c over wavelength. So that's how you can find the energy of a photon if you're given the wavelength of that photon. So let's say if we have a hydrogen atom. So let's say this is the nucleus of the hydrogen atom. What happens if an electron in the second energy level, if it falls to the first energy level? So each circle represents an energy level. This is n equals 1. That's the first one. This is the second. And this is the third. So if an electron goes from the n equal 2 energy level to the n equal 1 energy level. Will it emit a photon or will it absorb a photon? Anytime the electron falls down, if it moves closer to the nucleus, it's going to emit a photon. Now, if an electron, let's say it jumps from the second energy level to the third energy level, the only way an electron can jump to a higher energy level is if it absorbs a photon. So, anytime the electron absorbs a photon, it gains energy and it's going to jump to a higher energy level. If it falls down to a lower energy level, it's going to release a photon. So how can we calculate the energy of the photon that's absorbed or emitted whenever an electron within a hydrogen atom either falls down an energy level or if it jumps to a higher energy level? How can we quantify the photon's energy? Now, there's an equation that we can use to figure this out. And here it is. Its E is equal to negative 2.18 times 10 to the negative 18 joules, and then 1 over n final squared minus 1 over n initial squared. So you can use that equation to find the energy of the photon that's emitted or absorbed by the electron whenever the electron moves from one energy level to another energy level. So let's say if an electron moves from the fourth energy level to the second energy level compared to the third to the first, which transition releases more energy? Is it from 4 to 2 or 3 to 1? Typically, if you look at the final state, the smaller the final state is, the greater the energy change. Even though the difference seems to be 2 for both of them, whenever you fall to the ground energy level or the ground state, it releases more energy than any other states. So going from the third level to the first level is going to release more energy than from the fourth to the second. To see this conceptually, let's say this is the hydrogen atom, and let's say this is the first energy level. The second energy level is very far from the first energy level. Now the third energy level is not as far compared to the distance between the first and the second. So the third energy level is somewhat close to the second. And the fourth energy level is even closer. So after that, each successive energy level becomes closer and closer and closer. The energy difference between the first and the second energy level is a lot greater than the energy difference between the third and the second. So a transition going from the fourth energy level to the second will release less energy than a transition from the third to the first. As you can see, the distance between the third energy level and the first energy level is much greater than the distance between the second and the fourth energy level. Now, if you're ever unsure, you can use the equation to get the answer. So here's how you use it for these types of problems. Notice that this constant is going to be the same. So the only part that's going to be different is this portion of the equation. So let's use that portion of the equation and see which one is going to give us a higher value. So this is n initial and this is n final. So using that equation, 1 over n final squared minus 1 over initial squared. Is it greater than or less than 1 over 1 squared minus 1 over 3 squared? So if you use a calculator, 1 over 2 squared is 1/4, that's 0.25. And 1 over 4 squared, which is 1 over 16, that's like 0.0625. So if we subtract those two numbers, we're going to get a value of 0.1875. Now 1 over 1 squared is 1, which is much bigger than 0.25, 4 times as big. And 1 over 3 squared is pretty small. That's 0.111. So 1 minus 0.111 is about 0.889, which is much bigger than 0.1875. So that's why an electron transition from the third energy level to the first involves a greater energy change than if an electron moves from the fourth to the second. Now, there's another equation that you might need to know. It's called the de Broglie wavelength equation. And you can calculate the wavelength of an object by taking Planck's constant and dividing by the momentum of the object. Momentum is mass times velocity. Now, the wavelength has the units in meters. Planck's constant is joules times seconds, and velocity is meters over seconds. The mass in this equation is not grams. In fact, it's in kilograms. 1 joule is equal to a kilogram times a meter squared divided by a second squared. So therefore, whenever you have joules, and if you have mass as well, the mass has to be in kilograms, not grams. So now let's try some practice problems. Calculate the frequency and energy of a photon that has a wavelength of 200 nanometers. So first, let's find a frequency. So c, the speed of light, is equal to the wavelength times the frequency. Solving for v, the speed of light divided by the wavelength is equal to the frequency. So the speed of light is 3 times 10 to the 8 meters per second, and the wavelength is 200 nanometers, but we need it to be in meters so that it can match with meters per second from the speed of light. So keep in mind, 1 nanometer is 10 to the negative 9 meters. So now meters is going to cancel, and we're going to get the units for frequency, which is s to the negative 1, or 1 over seconds. So if we divide, so right now we have 3 over 200, but let's modify that. What's going to happen if we move the decimal 2 units to the right, to the left? Whenever you move the decimal to the left, the exponent is going to increase. So since we're moving it 2 units to the left, it's going to increase by 2. So negative 9 plus 2 is negative 7. 3 divided by 2 is 1.5. And we have 10 to the 8. And what I'm going to do now is take this number and move it to the top. So it's going to be 10 to the 7. So we can add the exponents. So the frequency is 1.5 times 10 to the 15. So the units for frequency is hertz. So now let's use that to calculate the energy of the photon. So E is equal to HV. So that's we'll round it to 6.6 times 10 to the negative 34. And let's multiply that by 1.5 times 10 to the 15. 1.5 times 6 is basically 9. So this is going to be about 9.9. And if we add the exponents, negative 34 plus 15, that's the same as 15 minus 34, which is negative 19. And so that's going to be the energy of the photon that has a wavelength of 200 nanometers. So go ahead and try this problem. Calculate the wavelength of a photon that has 3.3 times 10 to the negative 18 joules of energy. How would you do this problem? So we can use this equation. E is equal to hc over lambda. So if we multiply both sides by lambda. These will cancel. And so the energy times the wavelength is equal to hc. And solving for the wavelength, we can divide both sides by E. So now we have this equation. The wavelength is equal to Planck's constant times the speed of light divided by the energy of the photon. So let's go ahead and plug that in. So Planck's constant is 6.6 times 10 to the negative 34. And the speed of light is 3 times 10 to the 8. And the photon has an energy of 3.3 times 10 to the negative 18. So 6.6 divided by 3.3, that's 2. And we can move this to the top. So 2 times 3 is 6. So we have 6 times 10 to the negative 34 times 10 to the 8 times 10 to the positive 18. Keep in mind, whenever you move a base from the denominator to the numerator, the exponent has to change sign. In this case, it's going to change from negative to positive. So now we can add the exponents. Negative 34 plus 8 plus 18. 8 plus 18 is 26. So negative 34 plus 26, that's the same as 26 minus 34, and that's negative 8. So the final answer is 6 times 10 to the negative 8, and that's in meters. But sometimes we may need to convert that into nanometers. So let's go ahead and do that. Now keep in mind, 1 nanometer is equal to 1 times 10 to the negative 9 meters. So let's put the meters on the bottom so that these units will cancel. And we're going to place 1 nanometer on top. So we got to divide these numbers. 6 divided by 1, well, that's just 6. And so we can move this to the top so that the negative exponent will now be positive. So what we have is 6 times 10 to the negative 8 times 10 to the positive 9. If we add negative 8 plus positive 9, that's equal to positive 1. So the answer is 60, or 60 nanometers. So that's the wavelength of the photon. Try this problem. Calculate the energy of a photon released if an electron in a hydrogen atom falls from the 4th to the 1st energy level. So let's use this equation. And all we got to do is simply plug in the values into the equation. It's not bad. You just have to know this equation. So we need to know what n final and n initial is. The initial energy level is 4. The final is 1. So it's going to be 1 over 1 squared, which is 1, minus 1 over 4 squared. So 1 over 1 squared, that's basically 1, which is 16 over 16. And 1 over 4 squared is 1 over 16. So that is equal to 16 minus 1 is 15. So this is 15 over 16. So it's going to be negative 2.18 times 10 to the negative 18 joules times 15 over 16. 15 over 16 is just under 1. So we can estimate the answer as being about 2 times 10 to the negative 18 joules. It's going to be just under 2.18, but let's use a calculator. So 2.18 times 10 to the negative 18 times 15 over 16. The actual answer is about negative 2.04 times 10 to the negative 18 joules. So if we estimated and said it was 2 times 10 to the negative 18, that would have been a good estimation. So that's how you can calculate the energy of a photon released whenever an electron jumps from one energy level to another. So consider the following electron transitions. On the left side is going to be the initial energy level and the final energy level. So let's say if an electron falls from the 3rd energy level to the 1st, and let's say if it falls from the 4th to the 2nd, or from the 6th to the 3rd. So anytime the electron falls to the first energy level, it's associated with the Lyman series. And if it falls to the second energy level, it's called, or it's part of the Balmer series. And if it falls to the third energy level, it's related to the Paschen series. Now, for the Lyman series, whenever an electron falls to the first energy level, ultraviolet light is emitted. And for the Balmer series, the electron is going to emit visible light. So I'm going to put VIS for visible. This is like green, blue, yellow, orange. Anytime the electron falls to the second energy level, it usually emits visible light. And if it falls to the third energy level, it usually emits infrared radiation. Let's try this problem. A ground state electron inside a hydrogen atom absorbs a photon that has a wavelength of 102.7 nanometers. Into what final state will the electron jump to? So, we need to use the wavelength to calculate the energy of the photon. Once we have the energy, we can use that to find the energy level that the electron is going to jump into. So let's use this equation so that we can find the energy directly from wavelength. So Planck's constant, that's going to be 6.6 times 10 to the negative 34. And the speed of light is 3 times 10 to the 8. And the wavelength is 102.7. But let's round that to 103, which is going to be times 10 to the negative 9. And that's meters. Keep in mind, 1 nanometer is 10 to the minus 9 meters. So what is 6.6 times 3? 6 times 3 is 18, and 0.6 times 3 is 1.8. 18 plus 1.8, that's like 19.8. So I'm going to round 19.8 up to about 20, and I'm going to round 103 a little bit down to about 100. So this is 100 times 10 to the negative 9, and what we have is times 10 to the negative 34 on top, and times 10 to the 8. So we can cancel a 0, and on top, negative 34 plus 8, that's negative 26. So we have 2 times 10 to the negative 26 on top, and 10 to the negative 9 on the bottom, which we can move the decimal 1 unit to the left, and so this is going to increase by 1. So what we now have is 2 times 10 to the negative 26 divided by 1 times 10 to the negative 8. So we can move this on top to make it positive 8. So what we now have is 2 times 10 to the negative 26 times 10 to the positive 8. And negative 26 plus 8, that's negative 18. So we should estimate the energy as being 2 times 10 to the negative 18 joules. So let's confirm our answer with the calculator to see if our estimation is close. 6.6 times 10 to the negative 34 times 3 times 10 to the 8 divided by 103 times 10 to the negative 9. The actual answer is about 1.92 times 10 to the negative 18. So our rounded answer is pretty close. So now, let's use this equation to calculate what final state the electron is going to jump into. So let's replace E with 1.9 times 10 to the negative 18. Now, is E positive or negative? Notice that the electron absorbs a photon. That means that the energy change is positive. So let's plug in positive 1.92 times 10 to the negative 18. Believe it or not, the sign matters. Now the final state, we're looking for it, so let's replace it with x. The initial state is the ground state, so that means that n initial is 1. Now we can cancel the 10 to the negative 18 because it's exactly the same on both sides. So let's divide both sides by negative 2.18. So these numbers will cancel. And at this point, I'm going to use a calculator. 1.92 divided by 2.18. That's going to be about negative 0.881. And this is equal to 1 over x squared minus 1. So let's add 1 to both sides. So negative 0.881 plus 1, that's going to be about positive 0.119, which is equal to 1 over x squared. So what would you do at this point to solve for x? So let's raise both sides to the negative 1. When you do that, you can flip it. So on the left side, it's going to become 1 over 0.119. And on the right side, instead of being 1 over x squared, it's x squared over 1, which is just x squared. So let's find out what 1 divided by 0.119 is. That's going to be about 8.4. So if we take the square root of both sides, the square root of 8.4 is about 2.9. So we can round 2.9 and say it's 3. So this is approximately 3. Keep in mind though, we rounded a few numbers. We rounded the 102.7 to 103, and also when we were solving it, we reduced it to 100 instead of 103. But 2.9 is close to 3 though, so it's going to jump into the third energy level. If we didn't round in the answers, this value should have been closer to 3. And you could try it with your calculator if you want. So now let's go over electron configuration. How can we write the electron configuration for nitrogen? Now, if you look at the periodic table, the atomic number for nitrogen is 7. So that means that an atom of nitrogen has 7 electrons total. Now, in the first energy level, you only have the 1s sublevel. In the second energy level, there's 2 sublevels, 2s and 2p. And in the third energy level, we have 3s, 3p, 3d. In the fourth energy level, we have 4 sublevels, 4s, 4p, 4d, and 4f. So notice that the sublevels is always equal to the energy level. Now, S can hold up to 2 electrons, the P sublevel can hold up to 6 electrons, the D can hold up to 10, and F can hold up to 14. So the first one is going to be 1s, so 1s2, and then after 1s comes 2s, so that's going to be 2s2. Now after the 2p sublevel, after the 2s sublevel, comes the 2p sublevel. Now the p sublevel can hold up to 6 electrons, but we only need a total of 7. Right now, if you add the exponents, 2 plus 2 is 4. To get to 7, we only need 3 more. So we're going to stop at 2p3. This is the electron configuration for nitrogen. Notice that the exponents add up to 7. So let's try another example. Let's write the electron configuration for aluminum. Aluminum has an atomic number of 13. So we need to get up to 13. So this is 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. We may not need to go that far. So in the first sublevel we have, or in the first energy level we have 1s, 1s2, and then it's going to be 2s2. After 2s we have the 2p orbital and then the 3s. But in a 2p orbital, we can hold up to 6 electrons. And in the 3s orbital, it can hold up to 2. Right now, we have a total of 2 plus 2 plus 6, that's 10, plus 2 is 12. We need one more to get to 13. So on the 3p level, even though it can hold up to 6 electrons, we're just going to have 1 electron in the 3p sublevel. So that is the electron configuration for aluminum. By the way, the video that you're currently watching is the 3-hour trailer version of a longer 7.5-hour video. So in that video, I'm mostly going to cover other topics in addition to electron configuration and quantum numbers. We're also going to go over Lewis structures, hybridization, molecular geometry, how to tell if a compound is polar or nonpolar, molality, molarity, mass percent, density, solutions, things like that. Phase diagrams, intermolecular forces, Raoult's law, Henry's law, colligative properties, and a lot of other stuff that's related to those topics. So I'm going to post a link, and you can check it out when you get a chance. And let's get right back into our lesson. Now let's try this example. Manganese. Manganese has an atomic number of 25. So feel free to pause the video and see if you can write the electron configuration for manganese. So let's make our list. 1s, 2s, 2p, 3s, 3p, 4, well, that's supposed to be 3d. And then it's 4s, 4p, 4d, 4f. So it's going to be 1s2, then after 1s it's 2s2. P can hold up to 6 electrons, so it's going to be 2p or 2p6, and then after 2p6 is 3s2. Then after 3s it's going to be 3p, then 4s. So it's 3p6, 4s2. After 4s we have 3d. So the d sublevel can hold up to 10 electrons, but we don't need all 10. Right now, 2 plus 2 plus 6 is 10, and 2 plus 6 plus 2 is 10, so we're at 20. We need 5 more to get to 25, so we're going to stop at 3d5. That is the electron configuration for manganese. Now let's go back to nitrogen, which had an electron configuration of 1s2, 2s2, 2p3. Now, how can we write the orbital diagram for this element? So this is going to be the 1s orbital, and then this is the 2s orbital, and this is the 2p orbital. So as you go up, the energy of the orbitals increases as you move away from the nucleus. So the 2p sublevel has more energy than the 2s sublevel. There's something called the N plus L rule. N is the energy level. So let's say for the 2p sublevel, N is 2. Now, for the S sublevel, L is 0. For the P sublevel, L is 1. For D, L is 2. And for F, L is 3. So keep that in mind. So if you compare the 2s sublevel with the 2p sublevel, so for 2s, N is 2, but L is 0. And for 2p, N is 2, but L is 1. So notice that if you apply the N plus L rule, for 2p you get a score value of 2 plus 1, which is 3. But for 2s, you get a score value of 2 plus 0, which is 2. So that means that the 2p sublevel has more energy than the 2s sublevel. That's why it's higher above it. And typically, in the electron configuration, the way you write it in order of increase in energy. So 2s has more energy than the 1s sublevel, and the 2p sublevel is higher in energy than the 2s sublevel. So let's add electrons to these sublevels. So according to the off-bar principle, when adding electrons orbitals, you need to fill the lower energy levels first before you fill the higher energy levels. So that means that we can't put an electron in a 2s before filling the electron in the 1s sublevel. So we got to start from the bottom and work our way up. So this is the first one, this is the second one. Notice that these electrons have opposite spins. One is up, the other is down. Two electrons cannot have the same spin when they're in the same orbital. Now, for the 2s sublevel, we need to add two more electrons. Now, notice that in the 2p sublevel, we have three orbitals, or three boxes. Each box represents an orbital. You can put them in boxes if you want. Now, notice that the three orbitals in the 2p sublevel are horizontal with respect to each other. That means that they have the same energy. So they're called degenerate orbitals. Degenerate orbitals are those that have the same energy. Now, according to Hund's rule, whenever you're adding electrons to degenerate orbitals, you need to add them one at a time with parallel spins. So they need to be half filled before completely filling them. So according to Hund's rule, if you're going to add the first two electrons, you can't add them like this. You can't pair it up first. You have to add one arrow one at a time. So after you add the first arrow, the second arrow goes in the next box. And they're going to have parallel spins initially. So if the first arrow is up, the second one has to be up. So now if you're adding two electrons, because they share the same negative charge, they repel each other. So an electron doesn't want to share the same room with another electron if there's an empty room that's available. It prefers to have its own room, so to speak. So electrons, they prefer to be unpaired as opposed to being paired, and this minimizes electron repulsion. So according to Hund's rule, if there is degenerate orbitals, meaning if there's another orbital of equal energy, the electron prefers to fill that orbital first before pairing up with another electron. So the third electron is going to go here. Now the fourth electron has no choice but to go in one of these orbitals. But we're going to stop here because we only have three electrons in the 2p sublevel. So for nitrogen, this is how it looks like. So sometimes you might get a question where it asks you how many paired electrons are in the nitrogen atom, or how many unpaired electrons are there. So these electrons are considered to be paired. So we have 4 paired electrons. Now, how many unpaired electrons do we have? Each of these are unpaired electrons. So we have 3 unpaired electrons. Now, this material, nitrogen, is it paramagnetic or diamagnetic? Now, whenever you have an atom that has a lot of unpaired electrons, the material is said to be paramagnetic, since it has, in this case, 3 unpaired electrons. Whenever a substance is paramagnetic, it's weakly attracted to an external magnetic field. Now, if a substance has only paired electrons, it's said to be diamagnetic, and it's weakly repelled by an external applied magnetic field. Now, there are some materials that are ferromagnetic. The most common is iron. Iron metal is strongly attracted to a magnet, so iron metal is considered to be ferromagnetic. Now, let's consider the other example that we had, aluminum, which the electron configuration was 1s2, 2s2, 2p6, 3s2, 3p1. So how many paired and unpaired electrons are in aluminum? And also, is it paramagnetic or diamagnetic? So here's the 1s sublevel, and then 2s, 2p, 3s, 3p. The p sublevel always has 3 orbitals. S has 1 orbital, D has 5, F has 10. And each orbital can hold up to a maximum of 2 electrons. So the first sublevel is completely filled, and the same is true for the second sublevel and even the 3s sublevel. Now, in 3p, we only have one electron. So therefore, out of the 13 electrons that aluminum has, it only has one unpaired electron. So to find the number of paired electrons, subtract 13 by 1, and so aluminum has 12 paired electrons. 2, 4, 6, 8, 10, 12. Now sometimes you might get a question to ask you, how many p electrons does aluminum have? To figure this out, once you have the electron configuration, look at the 2p sublevels. You have 2p, 3p. So the 2p sublevel has 6 electrons and the 3p sublevel has 1. So aluminum has a total of 7p electrons. So now let's go back to manganese, which we said the electron configuration was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. So how many p electrons are in manganese? Looking at the electron configuration, we see that there's 2p6 and 3p6. So manganese has 12 p electrons. How many s electrons does it have? 2, 4, 6, 8. So it has 8 s electrons. And how many d electrons does it have? It only has 5 d electrons. Now, manganese, is it paramagnetic or diamagnetic? And how many unpaired electrons does it have? All you need to do is look at the last sublevel, because everything else below that is going to be filled. Now the 3D sublevel can hold up to 5 orbitals. It can have up to 5 orbitals, which means that it can have a maximum of 10 electrons. So according to Hund's rule, whenever we have degenerate orbitals, that is orbitals with the same energy, we need to add electrons one at a time to each orbital with parallel spins. So this is going to be 1, 2, 3, 4, 5. So therefore manganese has 5 unpaired electrons. Because it has a lot of unpaired electrons, it's going to be paramagnetic. Now manganese has a total of 25 electrons because the atomic number is 25, and for a neutral atom, the number of protons and electrons both equal the atomic number. So 20 minus 5 is going to give us 20 paired electrons. So now you need to know which elements are exceptions whenever you need to write the electron configuration. So on the periodic table you have chromium, and below chromium there's molybdenum. These are exceptions. And you have copper, silver, and gold. So let's go over chromium and copper. Write the electron configuration for chromium. Chromium has an atomic number of 24. So let's start with 1s. So it's 1s2, and then 2s2, and then the p sublevel can hold up to 2 electrons, so it's going to be 2p6, and then 3s2. After 3s, we have 3p, then 4s. So it's 3p6, and then 4s2. So keep in mind, we said the p sublevel can have 3 orbitals, and each orbital can hold up to 2 electrons. So 3 times 2 is 6. That's why p goes up to 6. The p sublevel can have up to 6 electrons and 3 orbitals. Now after the 4s sublevel, we have the 3d sublevel. But right now we have a total of 20. 2 plus 2 plus 6 is 10. 2 plus 6 plus 2 is 10, so we have 20. And we need 4 more. So naturally, we would expect that chromium should have an electron configuration of 4s2, 3d4. But it turns out that an electron from the 4s level is going to jump to the 3d sublevel. So it's going to be 4s1, 3d5. And let's understand why that happens. So here's the first configuration that we had. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Now, sometimes you can simplify this configuration using noble gas notation. The way this is written, this is called the ground state electron configuration. Now, if you want to write it using noble gas notation, if you go to the periodic table, if you look at chromium, it has an atomic number of 24. Now, if you look at the noble gases, the noble gas just before chromium that has an atomic number that's less than chromium is argon. So we can rewrite this electron configuration as being argon. Now, argon represents the first 18 electrons because argon has an atomic number of 18. So 2 plus 2 plus 6, that's 10, plus 2 and 6, that's 18. So the configuration of argon is from 1s2 all the way to 3p6. So we can replace this with argon. So after 3p6, we can write argon and then 4s2, 3d4. So that's how you can write the electron configuration for chromium using noble gas notation. Now, we said that an s electron is going to jump into the d sublevel. So it's going to be 4s1, 3d5. But let's see why. So here is the 4s sublevel, and very close to it is the 3d sublevel. The 3d sublevel is very close in energy to the 4s level. They're not that far apart, so it's very easy for an electron to jump from the 4s level to the 3d sublevel because the energy is so close. But keep in mind though, which one has more energy, by the way, 4s or 3d, and how can you prove it? If you use the n plus L rule, for the 4s sublevel, n is 4, and for s, L is 0, so 0 plus 4 is 4. And for the 3d sublevel, n is 3, but for d, L is 2, so we get a score value of 5. So 3d is slightly higher in energy than 4s. So let's put the electrons in this orbital diagram. So let's write the orbital diagram for 4s2, 3d4. So according to Hund's rule, whenever you add in electrons to degenerate orbitals, you need to add them one at a time with parallel spins. Now, in nature, atoms, molecules, electrons, they like to arrange themselves in a way to minimize their energies. They like to find the most stable state. So why would this electron, why would it want to jump to a higher sublevel? Why would it jump to a sublevel that's higher in energy than where it's at right now? Because 4s is lower in energy than 3d. The only reason why it would do that is to become more stable. Whenever a molecule rearranges itself, it does so to increase its stability. Rearrangements occur because an atom or a molecule can find a way to become more stable. So this electron jumps into that energy level to become more stable. So even though it's jumping into a slightly higher energy level, once it goes here, it's no longer repelled by this electron. So when it's paired up with the other electron in the 4s level, there's a lot of electron repulsions. And so by jumping into the 3d sublevel, it doesn't have those electron repulsions. And so that stability is more, there's more stability that's gained by going into the 3d sublevel than the stability that's lost by jumping into a higher energy sublevel. And so that's why the electron jumps into the 3d sublevel. It wants to be unpaired rather than being paired. It's more stable for an electron to be unpaired than paired. Electrons prefer to have their own rooms. So, the correct orbital diagram for chromium looks like this. It's 4s1, 3d5. So chromium has 6 unpaired electrons, which means that it's paramagnetic. So now write the electron configuration for copper and write the ground state electron configuration and the noble gas notation. So copper has an atomic number of 29. Keep in mind, this is another exception, by the way. So go ahead and try it. So we have 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, and 4f. So it's going to be 1s2, and then 2s2, and then after that 2p6, and then 3s2. After 3s it's 3p, then 4s. So 3p6, 4, that's a 6 by the way, 4s2. Right now we have a total of 20 if you add the exponents. We need 9 more. So this will appear to be 3d9. Now it turns out that one of the s electrons for copper is going to jump into the 3d sublevel. So the correct ground state electron configuration for copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, well 4s1 actually, 4s1, 3d10. So copper, it has a similar pattern. So an s electron jumps into the 3d sublevel. Now, how can we write the noble gas notation for copper? So the noble gas that's before copper is argon. Argon has an atomic number of 18, which is less than that of copper. We can't use krypton because the atomic number for that is 36, which exceeds that of copper. So we have to use argon. Now the electron configuration for argon ends in 3p6. If you add these numbers, 2 plus 2 plus 6 plus 2 plus 6, that is 18, which is the electron configuration for argon. So we can replace that with argon. So then what's left over is 4s1, 3d10. So if you add everything, argon is 18 plus the 1 plus the 10. You should still get a total of 29, which is the atomic number for copper. So this is the electron configuration using noble gas notation for copper, and that's how you can write it. So now let's go over the electron configuration for ions. How can we write the electron configuration for the aluminum plus 3 cation? Now for aluminum, which had an atomic number of 13, the electron configuration was 1s2, 2s2, 2p6, 3s2, 3p1. This is the ground state electron configuration. Now, the reason why this adds up to 13 is because aluminum has 13 electrons. How many electrons does the aluminum plus 3 ion have? Keep in mind, the number of electrons is the atomic number minus the charge. The atomic number of aluminum is 13, and if you subtract it by the charge of plus 3, aluminum has 10 electrons. So the exponents must add to 10. So therefore, we need to get rid of 3 electrons. So we need to get rid of the 3p1 electron and the 2 electrons in the 3s level. So the electron configuration for the aluminum plus 3 cation is 1s2, 2s2, 2p6. Notice that the exponents adds up to the total number of electrons in this ion, which is 10. So now write the electron configuration for sulfur and the sulfide ion. Now sulfur has an atomic number of 16, which means that it has 16 electrons. But how many electrons are in the sulfide ion? So the number of electrons is equal to the atomic number minus the charge. So the atomic number for sulfide is going to be the same as sulfur, is 16, and the charge is negative 2. 16 minus negative 2 is the same as 16 plus 2. So therefore, the sulfide ion has 18 electrons. Now the electron configuration for sulfur is going to be 1s2, 2s2, 2p6, 3s2, and 3p4. So basically you follow the same pattern as we've been doing, but you keep going until the exponents add up to 16. 2 plus 2 plus 6 is 10, plus 2 is 12, plus 4 is 16. So notice that we need 18 electrons for the sulfide ion. So we're going to add 2 more electrons to this number. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6. And so this is the total number of electrons in the sulfide ion, which is 18. But this is the ground state electron configuration. So we're going to try one more example in this regard. And that's the Fe atom, which has an atomic number of 26. And we're also going to write the ground state electron configuration for the Fe plus 3 ion. So it lost 3 electrons, which means that it has 23 electrons. So let's start with Fe. It's going to be 1s2, 2s2, 2p6. So we have a total of 10 so far. 3s2, 3p6, 4s2. So we have 20. So we need 6 more. So let's stop at 3d6. D can hold up to 10 electrons. Now, when we take off 3 electrons, do we need to take it off the 3d sublevel or the 4s2 sublevel? When you need to remove electrons, the electrons usually come off the higher energy level, which is the 4s level, before they come off the 3d level. So we need to take off both 2 electrons from the 4s level, but since we need to take a total of 3, we need to remove 1 from the 3d sublevel. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6. Now you can omit 4s, or you can write it as 4s0, and then 3d5. So if we add the exponents, 2 plus 2 plus 6, that's 10, plus 2 and 6 is 18, plus 5 is 23, which is the number of electrons. So here's a question for you. Consider these 4 ions: magnesium, sulfide, fluoride, and silicon. Now this is going to have a +2 charge, -2, -1, +2. Which of these 4 ions are isoelectronic to each other? So when something is isoelectronic, if you have 2 species that are isoelectronic with each other, it means that they have the same number of electrons, and therefore the same electron configuration, or at least the same ground state electron configuration. So which of these ions have the same number of electrons? So we can find the number of electrons by taking the atomic number and subtracting it by the charge. Magnesium has an atomic number of 12 minus 2. That means that it has 10 electrons. Sulfide, well, sulfur has an atomic number of 16 minus -2, which is 16 plus 2. So the sulfide ion has 18 electrons. So it's not isoelectronic with magnesium. Now for the fluoride ion, fluorine has an atomic number of 9 minus a charge of -1. 9 plus 1 is 10, so it has 10 electrons. Magnesium and fluoride are isoelectronic with each other. They have the same electron configuration, which is 1s2, 2s2, 2p6. These numbers add up to 10. Now what about silicon? Silicon has an atomic number of 14. And if we subtract it by the +2 charge, 14 minus 2 is 12. And so it's not isoelectronic with anything. So now let's talk about quantum numbers. There's 4 quantum numbers you need to know. The first one is n. N represents the principal quantum number. It's associated with the energy level of an electron. The second letter is L, which is the azimuthal or the angular momentum quantum number, which is associated with the sublevel. The next one is ML, the magnetic quantum number, and it designates the orbital within a sublevel. So those are like the boxes in the orbital diagram. And then finally you have MS, the electron spin, which can be one of 2 values. It can be +1/2 or -1/2. So if you have an up arrow, the electron spin is +1/2. and for a down arrow, it's negative half. So first, let's talk about the relationship between N and L. So in the first sublevel, not the first sublevel, but the first energy level, all we have is one sublevel, which is 1s. In the second energy level, we have two sublevels, 2s and 2p. In the third energy level, we have three sublevels, 3s, 3p, and 3d. And in the fourth energy level, there are four sublevels, 4s, 4p, 4d, and 4f. Now, what is the maximum number of electrons that can be in the first energy level? Because the first energy level only has the s sublevel, the first energy level can only hold up to 2 electrons. So that's the maximum number of electrons. What about the second energy level? Well, 2s can hold up to 2, but p can hold up to 6. So 2 plus 6 is 8. The second energy level can hold up to 8 electrons. Now what about the third energy level? D can hold up to 10. 2 plus 6 plus 10 is 18. And for the fourth energy level, F can hold up to 14. So 14 plus 18 is 32. So notice that the maximum number of electrons in an energy level is equal to 2n squared. So if you plug in 1 for n, 1 squared is 1 times 2, you get this number. If you plug in 2 for n, 2 squared is 4 times 2 is 8. If you plug in 3 for n, 3 squared is 9 times 2 is 18. And if you plug in 4 for n, 4 squared is 16 times 2 is 32. So knowing that, what is the maximum number of electrons that can be in the n equals 7 energy level? So the electrons is equal to 2n squared. So 2 times 7 squared is 49 times 2 is 98. So the 7th energy level can hold a maximum of 98 electrons. Now, what's the maximum number of orbitals the 7th energy level can have? Now keep in mind, there's 2 electrons per a single orbital. So therefore, the number of orbitals is half the number of electrons. So the maximum number of orbitals is equal to n squared. So 7 squared is 49. So therefore, in the 7th energy level, there are up to 49 orbitals. Now consider the third energy level, which we said there's the 3s, the 3p, and the 3d sublevel. S has 1 orbital, P has 3, and D has 5. So in the third energy level, which has 3 sublevels, there's a total of 9 orbitals. And as we said, the number of orbitals is n squared, and 3 squared is 9. So the equation works. Now, you need to know the shapes of the sublevels. S is spherical. It looks like a sphere. P has a dumbbell shape, and D has like a clover leaf shape. And F is just some complicated stuff that I'm not going to draw. Now, for the S sublevel, L is always 0. For the P sublevel, L is 1. For the D sublevel, L is 2. And for F, L is 3. So L is associated with the sublevel like S, P, D, and F. So, when n is 1, L can be 0, which corresponds to 1s. Now, when n is 2, L can be 0, or it can be 1, because we have the 2s sublevel and a 2p sublevel. When n is 3, L can be 0, 1, or 2. Because in the third energy level, we have the 3s sublevel, the 3p sublevel, and the 3d sublevel. So the number of sublevels always equal to the energy level. And notice that the maximum that L can be is always 1 less than n. So therefore, n is, or rather, L is less than or equal to n minus 1. So if n is 4, L cannot, I wrote 3, but I said 4. So let's say if n is 4, the most that L can be is up to 3. It can be less than or equal to 3. So that means it can be 0, 1, 2, or 3.